In an arithmetic sequence, the fifth term is minus 18 and the 10th term is 12. We want to find the first term and the common difference. If you go back to the very first video in this playlist, you will see how to get Tn of an arithmetic sequence. The first term is called A, the common difference is called D. We're given that T5, which is the fifth term, is equal to minus 18, so we plug 5 in for n here. We're given that the 10th term, which is T10, is 12, so we plug 10 in for n. So we get A plus 9D equals 12. You can see that we have two equations and two unknowns. We can solve between them to find A, which is the first term of an arithmetic sequence, and D, the common difference of the arithmetic sequence. The easiest way to solve these would be to take one of these equations and subtract the other. So if I take this equation and or if I take this second equation and subtract the top equation, whichever way you want to do it, it doesn't matter. Actually, I'll subtract them like this. A minus A is 0, 4 minus 9 is minus 5D, and we have minus 18 minus 12, which is minus 30. So D is equal to 6. So we get the first term A by, what I did was I took the top equation, minus 18 minus 4 times D. Minus 18 minus 4 times 6 is minus 42. So we found the first term A and the common difference D. In part 2, we want to find the sum of the first 15 terms. So the first term is minus 42. The second term is got by adding 6 onto it. Minus 42 plus 6 is minus 36. Then we add 6 onto this to get minus 30. Then 6 onto minus 30 gives minus 24, and so on. Notice, by the way, that the fifth term, T5, is minus 18, and the 10th term, T10, is 12. You can see here that I have 15 terms of the series written out. We want to get S15, which is the sum of them, and you can see that the whole thing cancels out down to 0. So S15 is 0. We can also use a formula for doing this. The sum of the first n terms of an arithmetic sequence or series is given by n over 2 into 2a plus n minus 1 times d. So n is 15, a is minus 42, so we have 2 times minus 42, which is minus 84, plus n minus 1, which is 14, times d, which is 6. Inside the square brackets we get minus 84 plus 84, which is 0. So that shows that S15 is 0. Parts 1 and 2 of question C were done in the previous video. So just look to the video before this, where I showed how to get the sum of the squares of the first n natural numbers using this identity here. I actually proved this identity as well, so both of these parts in the previous video. However, I want to look at part 3, which I didn't do, and we have the sum here, sigma r equals, this is 11, to 30 of 3r squared plus 1. Now I explained in the last video that we can write this as 3 sigma r squared from r equals 11 up to 30 plus sigma of 1 from r equals 11 up to 30. So we had an expression just like this. It was actually 6r squared plus 2. I showed could be written as 6 sigma r squared plus sigma of 2. So if you want to see why that is true, you can look to the last video. Now we can write sigma r squared from r equals 11 to 30 as sigma of r squared from r equals 1 to 30 minus sigma of r squared from r equals 1 to 10. Okay, so if we subtract off the first 10 terms from this here, then we're left with a term beginning with 11 squared, if we put in 11 for r, up to 30 squared. So we're left with this sum here. You see, if you write out sigma of r squared from 1 to 30, we'll have this series up here, and we want to subtract off sigma of r squared from r equals 1 to 10. So that's this series here. So we combine these and you see everything cancels out and we're left with the series starting with 11 squared and running up to 30 squared. That's what we want actually. That's this here. Now look at this here. I explained in the last video how to handle the sum of a constant. What does it mean? Well, we start with r equals 11. We plug 11 in here, but this is just a constant. So we just get 1, no matter what value r is. So when r is 11, we get 1. When r is 12, we get 1. When r is 13, we get 1. When r is 14, we get 1. All the way up to when r is 30, we get a 1. So how many 1s are there? Well, there are 20 1s actually. Okay, because this first term corresponds to r equals 11, and the last term corresponds to r equals 30. So you could imagine subtracting off 10 terms previous to that from r equals 1 to 10. So it's like subtracting 10 from 30. So we have 20 1s, which is just 20. 20 times 1 is 20. We just multiply the number of terms by whatever this number is. So we end up getting this here. But we can work out both of these sums using part 2, as we're summing from 1 up to some value n. So we can use this here. So this sum here has n equal to 30. So we used the result of part 2. We just plugged 30 into this. And over here, it's the same sum. It's the sum of the first 10. It's the sum of the squares of the first 10 natural numbers. So n is 10. So we plug 30 in for n here. So we'll have 30 times 31 times 2 times 30 plus 1, which is 61. Over 6, then we have a minus sign, and then we plug 10 in for this one. We have 10 times 10 plus 1, which is 11. 2 times 10 plus 1 is 21. Then you can go to your calculator and put in 30 times 31 times 61. And we have to subtract 10 times 11 times 21. I don't know why I put in a bracket. You don't need a bracket here. The multiplication is done first. And divide this by 6. So I'm just combining these two fractions. We then multiply by 3 and add on 20. I hope this is right, because if it's wrong I'll have to remake this video. So we get 27,230. We can check it by going here. We want sigma of 3r squared plus 1 from 11 to 30. And we get 27,230. 3 consecutive terms of an arithmetic series are 4x plus 11, 2x plus 11, and 3x plus 17. Find the value of x. Now, I'm calling these terms T1, T2, and T3. Now, they don't necessarily have to be the first 3 terms, of course. All that matters is that they are consecutive terms. That means that this term here comes immediately after this term, and this term here comes immediately after this term. That's what consecutive means. If we're talking about an arithmetic series, then this term minus the previous term should equal this term here minus its previous term. So we take T2, subtract T1, and we equate it with T3 minus T2. This would actually give us the common difference. Well, T2 minus T1 and T3 minus T2 is also known as the common difference D. Solving this, we find that x equals minus 2. As a check, we can plug x equals minus 2 into T1, so we get 4 times minus 2, which is minus 8, plus 11 is 3, so T1 should be 3. The next term is got by plugging minus 2 in here, so we have 2 times minus 2, which is minus 4. Minus 4 plus 11 is 7. Finally, we plug minus 2 into T3, so we have 3 times minus 2, it's minus 6. Minus 6 plus 17 is 11. Are these terms in arithmetic sequence or series? Well, they are. You can see that the common difference is 4. 7 minus 3 is equal to 11 minus 7. So d is equal to 4. We just need x. A finite geometric sequence has first term a and common ratio r. Now we're talking about a sequence here. So when we're talking about a sequence, we just separate each term by commas. We don't actually sum the terms. The first term is a. The common ratio is r, so the second term is ar. The third term is got by multiplying r by this. We get ar squared because we multiply by r each time. Ar cubed and so on. If you've forgotten how to get the nth term, you can find a pattern fairly quickly. T1 is a, T2 is ar, T3 is ar squared, T4 is ar cubed. We can see that the power of r is 1 less than the subscript of t. Or if you like, so if the subscript of t is n, then the power is 1 less than n, which is n minus 1. So the nth term, tn, is ar to the power of n minus 1. Now, we're given that this sequence has 2m plus 1 terms. In other words, n is equal to 2m plus 1. So, we are interested in the last term as question 1. The last term is going to be the t2m plus first term. So, here's our formula for Tn of a geometric sequence. So we just plug 2m plus 1 in for n. So we get ar to the power of 2m plus 1 minus 1, or ar to the power of 2m. So this is the last term. In part 2, we want to write down the middle term in terms of a, r, and m. Now, we need to recognize here that 2m plus 1 is an odd number. It's an odd integer. M, of course, is a positive integer. Has to be. Why is 2m plus 1 odd? Well, if you take 2m plus 1 and divide it by 2, what do you get? You get 2m over 2 plus a half. 2m can be divided by 2 because 2m is even, so we get m plus a half. In other words, when we divide 2m plus 1 by 2, we get m with a remainder of 1. So we get a remainder of this number when we divide by 2, which means we're talking about an odd number. So for example, 11 is an odd number. If we divide by 2, we get 5, remainder 1. If we have 13 divided by 2, we get 6, remainder 1. We always get a remainder of 1 when we divide by 2, when we divide an odd number by 2. To make this simple, let's start by supposing that 2m plus 1 is some small odd number, and we'll try and work out the middle term. Suppose 2m plus 1 is 5, so our terms look like this. T1 is a, T2 is ar, T3 is ar squared, T4 is ar cubed, and finally T5 is ar to the power of 4. Now where is the middle term? This is it here. So you can see that this is the last term of the sequence, which is ar to the 2m in general. But look at the powers of the middle term. The power of the middle term is half of the power of the last term. So we have to get half of 2m. Half of 2m is m. Now we could also see this more generally. Remember, the first term here could be written as ar to the power of 0, because r to the power of 0 is 1. So this is our middle term, as I've explained already using the simple example. But if we count the number of terms that are below ar to the power of m, what do we get? Well, we're going from 0 up to m minus 1. Well, 1 up to m minus 1 is m minus 1 terms, and then we add on this term, so we get m terms. How many terms do we have here? Well, if you look at 2m, 2m can be written as m plus m. So you see we're going from the term with the power m plus 1 up to the final term, which is a power m plus m. So we've a power m plus 1. The next term will be ar to the power of m plus 2, and then ar to the power of m plus 3, and so on. So we're going from 1, 2, 3 all the way up to m. So that's m terms. So we have the same number of terms below ar to the power of m as we have above ar to the power of m. Of course, all this only works because we have an odd number of terms, because 2m plus 1 is an odd number. Show that the product of all the terms of the sequence is equal to the middle term raised to the power of the number of terms. So let's get the product of all the terms of this sequence. So we have AR to the power of 0 times AR to the power of 1 times AR squared and so on, all the way up to AR to the power of 2m. So how many A's are we multiplying together? Well, there are 2m plus 1 terms in the sequence. So we have A multiplied by itself 2m plus 1 times. How many R's will we be multiplying together if we multiply all these terms? Well, we can forget about R to the power of 0, that's just 1. We have R to the 1 by R to the 2, all the way up to R to the power of 2m. How many R's is that? Well, that's just 2m R's. Well, all these A's are the same, so when we multiply A by itself, and we have 2m plus 1 of them, we just get A to the power of 2m plus 1, because we have 2m plus 1 of them. And what about R? Well, when we're multiplying all these R's, we add the powers. So we have 1 plus 2 plus 3 plus dot 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 plus 2m. So we want to show that this here is equal to the middle term raised to the power of the number of terms. Well, the middle term is AR to the power of m. And we want to raise it to the power of the number of terms. Well, we know that we have 2m plus 1 terms. So what do we get here? Well, we have a product inside the brackets, so we put each part of the product to the power. So we get A to the power of 2m plus 1 times R to the power of m to the power of 2m plus 1. We multiply these powers together to get R to the power of 2m squared plus m. So we want to show that these are equal. Well, we can see that the A's are the same, but we need to show that the R's are the same. To show that these R terms, the R part of it, are the same, we need to look at the powers. We need to show that 1 plus 2 plus 3 summed as far as 2m equals 2m squared plus m. So we need to look at this sum here. If you notice this series here, you'll see that it's an arithmetic series. That's the power here. The first term A is 1, the common difference D is 1, because 1 plus 1 is 2, 2 plus 1 is 3, and so on. And the nth term, n is 2m. Actually, the number of terms n is 2m, which happens to be equal to the nth term as well. So we want the sum of an arithmetic series. So here is Sn for an arithmetic series. So we are interested in S2m because for this series n is equal to 2m. We have the first 2m terms. So we put 2m in for n. For A we put in 1. For D we put in 1. 2m divided by 2 is m. Inside the bracket here we get 2 minus 1, which is plus 1, and we have a 2m. We multiply by m to get 2m squared plus m. So that shows that this quantity here, series, equals 2m squared plus m. So that shows us that the product of all the terms of this sequence is equal to the middle term raised to the power of the number of terms, which is 2m plus 1.